Hello, everyone. Thanks a lot for introduction. So I already presented for this seminar. I will skip introducing myself. I will go directly to the presentation. So in the chat, you have a link to the presentation slides, and inside you have links to all the demonstrations that I will be using during these two lectures, essentially. So I'll start sharing my screen. So usually when I give this lecture, I accept the questions throughout the presentation because the notions might be a bit confusing. So if something is not clear, I suggest you can interrupt me and ask and not wait until the end because you might forget what was the question. So let's start. We will talk about causal inference and causal learning. Essentially, how can we make causal conclusions from the data and more importantly from observational data? And this is something that we would like to do, and of course in the framework of machine learning as well. A brief outline of the presentation. So this will include today's lecture and the next week lecture. We'll cover, I guess, the first half today and more or less the second half the next week. In this presentation, there are three parts. The first part will be the introduction. We'll cover historical overview. We'll talk the mathematical formalization of the problem. We will see the first demonstration, and there will be a short overview of the field of causality and machine learning as a whole. Then the second part will be about causal inference. Essentially, how can we measure the strength of the causal effect when we already know the types of relationship between different attributes in the data set? And the third part, to me the most interesting, is called causal learning. And this part is about how to learn causal effect relationship, that is how to automatically identify which attribute is a cause and which attribute is an effect from observational data. So let's get started directly. We will start with introduction and some historical overview. And to begin with, I would like to discuss what is the cause. Because to work with something, we need to name it to be able to understand what we are talking about. And what is the cause is a sort of philosophical question as well. So you can find a lot of also literature philosophy that tries to identify, give some definition of cause and effect. But we need some mathematical definition because this is something that we can work with. And we will define the cause, or the variable will be considered as the cause of another variable if the change in this causal variable implies the change in the effect. So this will be our running working definition. We'll use an alternative name for the cause or the change. So we will also call it a treatment. And why it will become clear, I think, in the next slide or in the next couple of slides. Is this problem of measuring the cause and effect important? And of course, yes, there are numerous practical applications when we are interested in causal relationship and in the strength of causal relationship, but not just in measuring association. I would say in most of the cases, what we are interested in, when there is some association reported, we are interested in which fraction of this association is due to causal relationship. And here on this slide, we have a couple of examples. For example, the first one, we want to measure the effect of the climate change policy on the mission. Here, we are not interested in association. We are interested in causal relationship because we want to use it as a measure to fight the climate change, for example. Or what is the effect of some treatment on a disease? Again, we are interested in using this treatment as a way to fight the disease. So we need to have causal relationship between these two variables. Or what is the effect of social media on mental health? And there are many more others. A little bit about historical perspective. So though this direction is relatively new in the framework of machine learning, it is not then new in the framework of other sciences, and in particular social sciences, such as economics and sociology or medicine, for example. So these are the fields, and the researchers in these fields, they contributed a lot to the formation of this discipline, and this is what we are basing on now when we try to build causal machine learning. Why did it happen so? Well, because the questions that the scientists are working with in these fields are by nature causal questions. Some of those questions that we just saw on the previous slide. For example, in economics, we might be interested what would be the effect of tax increasing. So will it increase the overall wealth of the society or not? Or in medicine, what is the effect of a drug? So the questions, the nature of the questions they're working with is by definition causal. And the current trend is now to try to build causal machine learning. So the scientists from machine learning and statistics and computer science are trying to combine the forces, and with the aim to build something that we can call causal machine learning. This field, as I said, is heavily based on the results that were developed before in the social sciences. That is why some of the techniques that we will see today, you will see that their application is sort of natural in the framework of social sciences, but we can also use it when doing automatic analysis as being data scientists, for example. This field is still under the development, but there are already some practical results, and I think that is very important for every person who tries to do any form of data science to at least know that such techniques and such tools exist, because we can use them directly and we don't need to reinvent the wheel. So I would say, from my opinion, it is important to know which tools already exist and what are the theoretical and the practical limitations. So where we can do some causal conclusions, and in which cases we should know that we are not allowed to do a causal conclusion because we don't have enough of information. Probably most of you have heard this expression that association does not imply causation. And it is true in many cases. However, it is not always the case. And we will discuss essentially in the first 2/3 of these lectures, these two lectures, the cases when association can imply causation. So we will start first with the fact that there is an objective measure for causality if we have some data set. And for example, we want to measure the causal effect. There is no objective way to do it, no mathematical way to do it, because as we defined our cause is something for which the change in this attribute implies the change in the effect. Whenever we have a data set, it is already a static data set, so we cannot induce actively some changes. That is why there is no objective mathematical measure for causality. There is only a measure for association. So this is something that probably all of you know how to calculate from the data set, different ways of calculating association, correlation, and so on. Let us now discuss in which cases we can observe association in the data set. And there are 3 cases that I listed here. The first one is spurious associations. So these associations that we just observe by chance, and there is absolutely no relationship between the attributes. And here I give an example that is taken from this website, so you can go and check many more interesting examples. On this graph, we have 2 time series represented with red and black curves, and the red curve shows us the worldwide non-commercial space launches, the number of those through different years, and the black line shows sociology doctorates awarded in US, so number of doctorate diplomas awarded. As we can see from the graphs, the 2 time series, they have very similar trends. So most probably, if we now take any measure of correlation or association between time series, the coefficient will be very high. However, our common sense says that there is absolutely no link between these 2 events. So this should be just some spurious association. The second type of the case when we can observe association in the data set is confounding association. And as an example is presented here, confounding association is when we have, assume that this link doesn't exist, so we have some common cause, and then we have two other variables. And if the two other variables are caused by the same common cause, then naturally we will observe association between them. And the final one is when there is a causal relationship between two attributes, as presented on this figure. With the arrows, we'll be representing causal relationships. So there is some cause or treatment, as I said, and it is often represented with the letter T. And there is some outcome that is usually represented with the letter Y. And there is a causal relationship. And in case of causal relationship, except from some minor cases, we will always observe association. So now, what will be our strategy to identify causal relationship from the dataset? The strategy will be the following. We'll try to roll out all the possibilities that do not imply causal relationship. So we will be doing analysis of the data and we'll be proving ourselves that the association that is observed in the data set can be only explained by causal association. So we'll have to rule out, for example, the first case, that is the spurious association. To rule out this opportunity, it requires some domain understanding and domain knowledge. So there are no objective, universal, automatic techniques available for this. So we will skip this in this presentation because many times it requires domain understanding. As for confounding association, we will see in this lecture that it is possible to combat with this case. So we will be able to separate the confounding association from the causal association. And finally, this will be the purest case when all the association that is measured in the data set can be only attributed to cause. Now, let us talk about techniques, how we can identify and measure causal relationship. And the gold standard of measuring causal relationship is randomized controlled trials or experiments. And how they are designed? They are designed in such a way that we keep everything constant except our causal variable, the variable that we assume to be a cause, and we try to observe if there is any change induced in the treatment variable. So we'll be trying to follow this definition. So this type of approach always guarantees us that we will be able to identify the causal relationship, so who is the cause and who is the effect, and we will be also able to measure the true causal effect, that is the association that is only due to association and not mixed, for example, with confounding association or with spurious association. However, performing such experiments is not always possible, and we can have multiple reasons. For example, there can be ethical reasons. Assume that we want to measure the effect of smoking on the probability of getting the cancer. So here, to run an experiment, we would need to take a group of people and randomly split them into two subpopulations and assign one subgroup to smoke and another not to smoke. So this is unethical. We cannot do this. We cannot force people smoking. Second option, it can be possible in theory but infeasible in practice. Assume that we are interested in such a question. What is the impact of political regime on the economic development on the country? So in theory, we can imagine ourselves such an experiment when we randomly assign different political regimes to different countries. Imagine that we have some global planet superpower that can do it. However, it is infeasible in our practical realities. And finally, sometimes it can be just infeasible, impossible to even imagine any kind of experiment. For example, if we want to identify what is the effect of genes on cancer, as long as we don't have the mechanism to actively intervene and change the value of the genes, this is practically infeasible to do it. So here comes a question that we will be interested in. How can we identify causality purely from observational data? And as I said, we'll be trying to rule out different options from this list. We will not be considering this case because, as I said, will require some domain knowledge. We'll try to rule out this option. So we'll be concentrated on how can we remove confounding association. And now I will briefly introduce the idea of how we can do it, and later I will show you the formal proof. So what will be our strategy? Assume that this is our system. We have a confounder, we have our treatment or the cause, and we have our effect. So now the association that we will observe in our data set will be due to causal association and then confounding association that flow through these two paths. So we would want to remove this confounding association. What can be our strategy? Let us assume for simplicity that our attributes are all binary because it will make it the calculation and the explanation simpler. But later we will see that we can do the same thing for continuous variables as well. And assume, so our variables are discrete and they are binary. What we will do, we will now split the whole data set on two groups, depending on the value of the confounder. So in this group, the value of the confounder is equal to 1. In this group, the value of the confounder is equal to 0. What will be the result of this action? Remember our definition of cause. Again, I will come back to the very first slide. The cause, the change in the cause implies the change in the effect. In this subdata set, there is only one value of the confounder C. So there is no any change in the confounder C. So there is no way this confounder can have causal relationship on treatment or causal relationship on the outcome. So whatever is left is only causal relationship between T and Y in this group of the data, this sample of the data set. And the same thing in another. There will be no causal effect of the confounder on our treatment and the outcome, and the only thing that we will observe is the causal effect. So we can calculate the true causal effect, or I will use abbreviation ATE, and later I will explain what it means, average treatment effect. We can calculate it separately for C equals 1 and for C equals 0. So this is great. We have done it in subgroups. But now the question, what will be the true causal effect for the whole group? And the idea here is very simple. We will just combine these two values together with the weights. And the weights will correspond to the size of every subgroup. So this will be our strategy. And let us see how it works in practice with a small demonstration. So now you should be able to see my screen with the code, with the collab notebook. I will start running the notebook and we'll just explain some things on the way. We'll be using this library, Causal Graphical Models. And why? Because it allows us to define the model and then measure the true, then do some measurements of the causal effect and compare it with the true result. So let us see what is happening here. We're defining the model, and it is equivalent to the one that I have just shown on the slides. We have the common confounder C, we have our treatment or the cause T, and we have our outcome variable Y. This is the definition of the model. So C is a random binomial attribute, and it doesn't depend on anything. It is random. That is why there are no incoming edges to C. It has no causes. So binomial attribute generated with the parameter 0.5. So in half of the cases, it will be equal to 1. In half of the cases, it will be equal to 0. Then to define the variable T, we say it is a discrete model that depends on the incoming value of C. If C is equal to 0, then this line defines us how to calculate the value of t. T will have two possible values. So for the case c equals to 0, we'll observe t equals 1 with probability 90% and t equals 0 with probability 10%. If the incoming value of c will be equal to 1, then we observe inverse. So now t equals 0 with probability 90% and t equals 1 with probability 10%. And in a similar way, we can define y that now depends on two variables, t and c, and these are the distribution of probabilities. Again, there are two possible values of y, and depending on the incoming values of t and c, this is how we calculate it. So in this case, again, for input values of t and c, 0 and 0, we observe y equals 0 in 10% of the cases and y equals 1 in 90% of the cases. So this is how we can define the model. Here, what we'll be doing, this is sort of a simulation of randomized control trial. To understand a bit more how it works, you would need to dig into the library, but I will just give you a hint. So here we can actively set the value of t. And here I said like 5,000 will be equal to 0, 5,000 will be equal to 1. So I'm sort of simulating the randomized experiment. And because I have the full control of the model, I can do it. And this will allow us to calculate the true causal effect. Just a second. Yeah, this will allow us to identify the true causal effect. As I said on the slides, that when we perform randomized experiment, all the association that we observe in the data set can be explained only by causal association. So from here, what we will be doing, because our variables are all binary, this is the data set that we obtained from a randomized control experiment, and this library gives this data set as a data frame. Then we can take that part of the data set where our treatment equals to 0 and calculate the mean value of the outcome. So this is what will be the value of our outcome when the treatment is set to 1 by the experiment. And what is the value of our outcome when the treatment is set to 0 by the experiment? These two values that we get. And then, as we said, we take this difference. So the difference in the treatment should imply the difference in the outcome. Calculate this difference. And this is our true causal effect. So here it is almost minus 30%. This is the true causal effect. And now we'll discuss how we can try to reconstruct this value by having only observational data. So here I am generating a sample. We'll reduce the size of the sample. I'm generating a sample from the data set, from observational data set. So without any intervening, without any experiments. And the first thing that I suggest to do, so let us now try to do the same thing as we did for experiment. That is, split the data set into two parts where treatment equals 1, treatment equals 0, calculate the mean value of the outcome and take the difference and see how close this will be to the true causal effect. That is, how close the association from the observational data set will be close to the true causal effect. This is the method, this is the way that naively could be used to estimate the true causal effect, but as will be shown, it will give us incorrect estimation. So we did it here. We calculated the new values of, this will be called potential outcomes. I will introduce it later. So what is the value of outcome for a particular value of treatment? And we can compare it with the true values that we have just computed above. And we can see what is the error of our estimation. Here it is almost 62%, and here it is 22%. Then we can take the difference between these two numbers and calculate our estimation of the true causal effect. And again, calculate the error by comparing it with the true AT that we computed above with the simulation of randomized experiment. So let us see, it was minus almost 30%. And this estimation gives us minus 38%. So our error of estimation is minus 27, almost minus 28%. So association here is not the same as causal relationship here. Now, let us try to use that technique that I just presented on the slide, and it has a name, backdoor adjustment, and later you will understand why it is called that way. So what we're going to do, we're going to split our data set into two parts, depending on the value of the confounder, C. So this is the first part, and then the second part. Then, as I said, we will need the sizes of these parts as weights to combine our estimations of the true causal effect inside every piece. To make it easier, the calculation, instead of as weights, we'll be using the probability. So I will take the size of this part of the data set and I will divide it over the size of the whole data set. So the probability of C being equal to 0 and probability of C being equal to 1. We'll use these values as the weights later. Now, what we are going to calculate these potential outcomes. So we calculate this potential outcome on the sub-data set where C equals 0 and multiplied it by corresponding weight, and the sub part of the data set where C equals 1 and multiplied by the corresponding weight. Potential outcome for treatment equals 1, so this is the treatment equals 1, and the same thing for treatment being equal to 0. So this is our new estimation of the, just a second, yeah, I will rerun it from the simulation. So we got it, and now again we can compare with the true causal effect that we know, and now our error is reduced. So we had 62% and 22% error, and now our error is almost 4% and less than -1%. And then we can calculate the true causal effect and compare, our estimation of the causal effect, compare it with the true causal effect. And now it is minus 31, almost 32%, and our estimation error is almost minus 7%. So it's already great. We reduced our error from 30% to 7%. Question, can we do better? And as usually in statistics, increasing the sample size helps. So let us try to generate a larger sample, but from the still observational data, and let us see what we'll get. Great, so we were able to reduce our error from 7% to 1. And as usually in statistics, when we'll be increasing the sample size, if it is possible from our analysis, we'll come closer and closer to the true estimation. Now I will ask, are there any questions?
I have a question about this error. This is the error between the percentages, right? Like a...
No, yeah, this is the error between the true causal effect, that here it is represented is in a fraction, but I used to call it in the in percentage. So here, for example, the error will be the relative error between our estimation, this is it, and the true causal effect that we calculated here. Does it answer your question?
Okay, yes, I understand.
Okay, great. Let's continue. Do you see my screen now? Okay, I will try once again.
Yes, we saw it twice, but now it disappeared.
Okay, I will try once again. Now we'll discuss. Yeah, great. Okay, we'll discuss a little bit thing known as fundamental problem of causal inference. What it is about. Whenever we want to measure the causal effect, we said that we can run experiments, but this is essentially already a substitute for a perfect experiment. And the perfect experiment will be to take the same item and try to see what happens when we change the effect, or when we change the value of the treatment. So here, for example, if we want to measure the effect of having humans on the planet, let's say t equals 0, there are humans on the planet, and t equals 1, no humans on the planet, on the climate change. Ideally, what we want to have, would want to have the two copies of exactly the same planet. It's like a parallel universe. For one, we assign having humans, and for another, we assign not having humans, and then we can do some comparison. So this will allow us to measure so-called individual treatment effect. So what is the treatment effect for this particular planet, for this particular instance? Of course, in reality, it's not always possible. Let us even imagine a very simple case. We want to measure the effect of a drug on the headache. And we take the same person. Today he has headache. We give him a pill and we observe what happens after that. Then the next day, again, he has a headache, but we don't give the pill. We observe what happens and we compare the two results. However, this comparison will not be already correct, because there is some days have passed, and the person as he was 2 days back is not the same as he is today. Some other processes inside the body might have occurred. So in measuring individual treatment effect is very difficult. That is why we also measure in experiments something that is called average individual treatment effect, or ATE. So we'll be measuring the expected value of the change in the potential outcome. So we already saw with you, with the code demonstration, we saw backdoor adjustment, or ATE formula. And now we'll talk a little bit of how we can prove it mathematically, let's say. To make any sort of causal conclusions, as we said, like this is our situation, when we can observe association. There are multiple possible cases. This will not consider, let us say, there might be confounding association or causal association. Purely from data set, if we don't know the structure, purely from the data set, we can measure only association, and it can be mixed from the confounding association. So how do we separate it? We will need some additional assumptions to claim that our conclusions can be considered as the causal conclusion. In fact, the whole theory of causality is about assumptions. Essentially, these assumptions will allow us to roll out all other possible cases except the one where association can be explained by the causality. So the whole idea will be essentially about assumptions. To use this approach that we have just discussed, 4 assumptions should be satisfied. The first one, no interference. It means the following: my outcome is the function of my own treatment. It means that my outcome doesn't depend on the treatment that another person receives. Let us consider an example to see how this assumption can be violated. Assume that we want to measure the effect of having a dog on the happiness. In this case, assume that when I have a dog and my friend as well has a dog, my happiness will be even larger than just me having a dog. Why? Because now we can spend more time with my friend, for example. So here there is an interference between my treatment and the treatment that was assigned to my friend. So the association that we will measure, it will be a mix of causal association of me having a treatment, but also of effect of my friend having a treatment. The second one, unconfoundedness. So no unobserved common causes. I just presented you the case, what we can do if we observe the common cause in the data set. So there is a column for confounder that specifies what is the value of the confounder. However, in many cases it can happen that we know there is a common cause, but we cannot measure it. We don't have it in our data set. So this is, in this way, this approach that we saw will not work. Will not be able to split data sets in 2 pieces depending on the value of the confounder. Second one is positivity. Positivity seems to be very innocent, but we'll discuss now why it is also important. So both, if we are talking about binary variables, we should be able to observe in the data set all the cases when both treatment equals to 0 and treatment equals to 1. And why it can be important? Because these two assumptions, they're sort of interrelated. Assume that we have multiple causes, common causes, sorry, or confounders, they are also called confounders. So now our strategy will be to split the data set according to all possible combinations of the values of our confounders. So if it is AXC, we'll have one split like this, another split like this, and so on, for all possible combination of values. However, the further we split our data set, the more chances are of the fact that we can violate the positivity. Because in some small part, we can have no observations, for example, for t equals 0 or t equals 1. And the final one is the consistency or uniqueness of the definition of the treatment. Mathematical formulation is that the observed outcome is the potential outcome under the treatment. What it means that if I have y conditioning on the value of treatment, for example, equals 1, from the observational data, I take the expected value, then I will have the potential outcome for this value of the treatment. When can it happen? This can happen when the treatments are not well defined or there are multiple versions of treatment. For example, we'll be measuring the effect of having a car, if the person is happy or not, or some other metric. And assume that we can give a good car, like a good car, and not very good car, a bad car, to a person. If there are, so to some people we assigned having a good car, and to others we assigned having a bad car. And of course, experience of having an old car might be even detrimental. So the person might have more problems of repairing the car and so on. And the effect will be different. So when we will be now measuring our effect of having a car, like y of t equals has car, when we'll be observing, what we'll be observing in the data set is y given t equals good car, or y equals t equals given t equals bad car. So these two things are not what we are interested in. This is when consistency can be violated. But if we have these four assumptions, we can prove mathematically the AT formula that we have just used with you. So let us go through this proof. This is what we start with, our average individual treatment effect, expected value between the potential outcomes. One more small note. When we have this notation with parentheses, we'll be talking about potential outcomes. So what would be the value of the outcome if I actively set the value of treatment being equal to 1? So this is something, notation of a randomized experiment, for example, that always give us the true causal effect. What will be our goal? Our goal will be to convert such mathematical expression that contains potential outcomes into a value that has only statistical values, some estimations. And if we can do it, we say that the causal quantity can be identified from a purely observational data set. Because all these statistical quantities can be calculated from the data set. And these require running an experiment. So let us do it. And the first assumption that we will be using is no interference. My outcome is the function of my own treatment. And this is required even at the stage of the definition of what is potential outcome. Then we'll use linearity of expectation, and essentially we'll open the brackets. So now we have the difference between two expectations. Then we'll use law of iterated expectations. So we will add conditioning on values of the confounders. Second. We'll be conditioning on these confounders. So what we are going to do, we condition on the confounders and then we marginalize over these confounders. So law of iterated expectations, if you're not familiar, just check online. Now, so what happened here? We just conditioned on the values of x. Now we'll continue using our assumptions. First, we'll use unconfoundedness and positivity. And essentially what we did here, we are adding the value of the treatment and as one more conditioning. And here, because we have positivity, we observe all of them. And because we have unconfoundedness, as we saw, when we condition on the confounders, additionally conditioning on the treatment, that is calculating what is the potential outcome for different values of treatment, give us the true causal effect. This is something that we just saw in the demonstration. And finally, we'll use consistency. Consistency is defined like this, as I said, y given the value of treatment equals 1, so we have expected value, this equals to expected value of the potential outcome for this value of treatment. So this is the transition that we made here. So we removed these potential outcomes, and now we have only statistical quantities. So this is it, and this is the formula that we essentially used in the previous demonstration. Any questions?
So this we can do only for a single confounder, right?
No, as I said, there may be multiple confounders, as here, A and C, 3 of them. Then we'll be splitting our data set for, on the subgroups for all possible combinations of the confounder values. Before, all possible combinations were C either equals 0 or equals 1. And now, if we have 3 binary confounders, we'll have 8 possible combinations. So 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on.
Okay, so we need to check them all together. I mean, can we check them one by one, or if we have multiple suspected confounders or expected confounders to be checked, do we need to check them all together and have this exponential growth of the possibilities?
So the thing here, what we're talking right now about is measuring causal effect when we know the structure. We'll talk about the case when we don't know the structure in the final part of the lecture. But when we know the structure, we know how many confounders we have. So like here, for this graph, I know there are 3 common causes. So I don't need to check them. I know how many of common causes there are. To use this ATE formula, also known as the backdoor adjustment, I just split my data set into the pieces according to different values of different combination of values of my confounders. I calculate ATE separately in every piece of the data set and then combine it together with the weights, as we saw here. There will be just more groups. In this example, we saw there were 2 groups, but for 3 binary confounders, there will be 8 groups. Does it answer the question?
Yes, and for 10 of confounders will be more than 1,000 groups, right?
It depends on how many values. Like even here, if you would have not binary confounder, but I don't know, with 5 possible values, it would be already more. This is where the positivity comes into play. But we will discuss later that there are other options. Like we don't always have to use the ATE formula. There are other options as well.
Okay.
So now is the time for discussion, but if we don't have questions, maybe I just continue presentation.
Maybe I guess that do you have it split at this point for the next lecture, or
I would need more time, I guess. So if possible, yeah, I would prefer to continue. At least I want to finish these 2 slides. Yes, these 2 slides I want to finish. So now let's talk about Simpson paradox. And the statisticians know about it, and I know that some in the audience know about it. What it is about, the Simpson paradox is measuring some statistical quantities, and when we measure it for subgroups, we have one conclusion, and when we measure it for the whole entire population, we have an opposite conclusion. Here is an example taken from the Wikipedia, and we have here the effect of treatment on the and the disease is the kidney stone problem, and there is also stone size, and there are 2 variants of treatment A and treatment B. Now, if we analyze the whole data set, not taking into account partitioning according to the stone size, then what we have? The percentage of recovery for treatment A is 78%. Percentage of recovery for treatment B is 83%. So treatment B seems to be preferable. However, if we now split this data set into subgroups for small stone size and for large stone size, and we do the calculation, we get in rows that for every group, treatment A is more preferable. And you can check that these numbers are all correct. You can just repeat this calculation by following this link. I will not be showing now. So you can prove yourself that all these numbers are correct. So how can this happen? For every subgroup, treatment A works better, but when we put the groups together, treatment B seems to be better. So this is a paradox that doesn't have an obvious answer. However, the theory of causality allows us to propose a solution to this paradox. And it depends on the causal structure of the problem. So we can have two possible structures. For example, like this: the treatment, A or B, the outcome, the fraction of recovery, and the stone size. If the stone size is the confounder, we just saw what we have to do. We need to split the data set into two groups and calculate separately and then combine the outputs. So in this case, we know that the A is better. However, if for such type of graph, when the stone size is impacted by the treatment, imagine that one treatment is, you have to wait for it longer. For example, it is in a stock in a different part of the country. And while you are waiting, your state becomes worse. So in this case, the stone size can be impacted by the treatment. In this case, so the S is not the confounder. There is causal association flowing according to both paths, and we should be analyzing this case. So in this case, B will be better. So causality gives us a solution to the Simpson paradox. Now, a small overview of the field of the causality in general. There are three pieces known as causal inference, causal learning, and representation learning. Causal inference is the case when we know the true causal graph. That is, we know what are the attributes and we know the relationship, the causal relationship. They are known. The question is how to measure the causal effect. And we saw with you one of the problems when we have common confounder, and we can, if it is observed, we can use the backdoor adjustment or ATE formula to calculate it. So this part is more or less solved. There are even automated tools that allow us to do some inferencing. However, for some particular cases, we still need to do manual analysis. Then there is a second part, causal learning. This is the case when we have the attributes, but we don't know who is the cause and who is the effect. The question is, how do we infer causal relationship from the data set? So this we'll already discuss now. This will be also discussed in the second part of the presentation. And this will be discussed in the third part of the presentation. What are the available techniques that allow us to identify the causal structure? And finally, there is a part known as representation learning. So in this case, we don't know neither the attributes nor the relationship between them, but we want to learn them from the data. An example of such an abstract task can be the following. So if we, as humans, we observe this picture, we already know who is the cause and what is going to happen. The bottle might fall. But for a computer, this is just a matrix of pixels. So the computer has to identify the relevant attributes and the relevant causal relationship between them. This direction of causal machine learning is still in its very infancy, and there are only a little bit of some preliminary results. I will not be at all talking about this part in this course, but I give at the end some links to and references that you can use if you are interested in this direction. So I will stop here. And we'll continue next week. Are there any questions? Would you like to discuss something?
So thank you, Marharyta, and let's open the questions. Just switch on your mic and ask questions if you have any. I have one at least. maybe just to initiate, I was thinking about maybe it is a bit related to this cat example, which is shown on the previous slide. I was thinking about feedback systems in which you have a mutual dependency or causality. Let's say that if you switch the in both sides, if you switch the color of this bottle, perhaps the cat will not throw it down, and so maybe the color of the bottle is causing the cat throwing this down, or this kind of or maybe you have this friend and a dog, and if you buy a dog, your friend will also buy a dog, and vice versa. So
yeah, so I think your question is about if we have two attributes, how do we know who is the cause and who is the effect? Yes, this is more about that.
And they both could be cause and effect at the same time. If you have a feedback system that if you change one, if you change A, the B will adjust to A, and vice versa.
Yeah. Okay, I see. Time. So we'll talk about it the next time, but the general theory of causality is built for such type of structure that is known as directed acyclic graph, so graph directed and without cycles. The general theory is built for that. However, we can consider this case by splitting it into two graphs for the timestamp. This is, for example, timestamp 0, and then the next timestamp will be the loop. So it can be extended to this case, but we will be considering this the theory for the case of acyclicity.
I see. Thank you.
Any other?
I guess maybe some of us will need to hear the presentation again slowly to embrace all the information that you passed here.
Okay, yeah, then we can discuss next time.
So if there is no questions today, I will thank you, Marharyta, for a very interesting and thought-provoking presentation. I will upload this recording, the link to the recording presentation on the website of the seminar, so everybody can access this if he or she wants, together with the link to the Colab code. And so thank you again, Marharyta, and I would like to invite you for the next week for the second part of the lecture. And so have a nice day, and see you next week.
Thank you for having me here, and hope to see you next week. Yeah.